Hey people, this is Jan. I'm going to talk about shaders today. First off, I want to talk about vertex shaders. Then right after that, it's going to be pixel shading, and talk about some of the passes that's going through the code. After that, I'm actually going to show you a piece of code and some works in Unity. With a problem that I want to work with, which is reflection and refraction. Yeah, I think we probably should get started. First off, we have made a fine presentation here, so we might just get that up running. Vertex shaders. So vertex shaders are basically operations that are executed once per vertex. So the input they are working with is, of course, vertex, normal texture coordinates, and uniforms. Output-wise, they are using a projected vertex, the vertex color, and other similar details. This is done this is used to actually transform the vertex position in 3D to 2D, while they're using the z-axis as depth. If we look at it from a pipeline viewpoint, vertex shader often happens in the geometric stage, where all the transformation, lighting, and so forth occurs. All this info is then parsed through vertex shading. All the information that is parsed through vertex shading is used during the rasterization stage, where we basically build the triangles. The triangles that we are working with in Unity, and for that sake, with all polygon models. And the reason why we do this is actually to see which pixels in the rasterization stage that is covered by these covered by it. These are then passed on to the fragment shader, which is the next part I'm going to get to, which is pixel shader, also known as fragment shaders. They basically take pixel and fragment positions, also information from all from the vertex shaders, and also uniforms again. Of course, I'll come into uniforms a bit later in it when I'm explaining, so just hold out. And the output that we're getting is actually color and depth. If you look at it, we can look at it as I'm gonna say pixel shaders work very differently from vertex shaders, where pixels are working more with the fragments, as I said earlier, because vertex, of course, work with triangles. As I said, they can output color, they can output a lighting value, and more, such as it's used for like bump mapping shadows, specular highlights, and other such things. I was going to say, it was like pixel shaders do have knowledge about the screen coordinates being drawn, and can what do you call it? Forget about it. It's completely. I'll probably remember it in a bit. So I won't take too much about it. We can use it actually for. We can also use pixel shaders for something like blur, edge detection, and also for use in if we want to cell shade or cartoon shade. And of course, since we have the fragments, they have different colors, and if they're not covered entirely by the triangles, some part of that fragment is going to be like chopped off and have another color. That's why we can blend it, so we actually mix the colors, so there's actually a better transition between those colors. I think that's enough about pixel shaders. Passes. Talk briefly about it before I actually go to the code and actually show some passes. Passes can basically be used to. They're actually basically a sub shader. So the amount of passes that you actually need depends on whether or not your shader that you are working with. If we take a sample from what is it called, specular highlight. The first pass is used to handle a main light source, and the second pass is used for the second pass is used as a second or additional source light, meaning that if you actually add more lights than just one, it will compile the other part. So it's basically a passes can be seen as a list of setups that handles or you could say it's the pass basically just handles an optional list of setup commands. With that said, I will go on to show what I decided to work on, reflection and refraction. And here, and first off, I'll just talk a bit about it. Here we go. Here we are in Unity and already have two objects running. Refraction and reflection. This way, the cube is our reflection. It's probably hard to see the difference right now, but I'll show in a bit why the difference is. And that one is the refraction. So we do know about refraction and reflection in the real world. Reflection, yeah, I think pretty much everybody knows about, like metallic surfaces and all that, and to a certain degree glass as well. But metallic surface, mirrors, for example, it's basically what do you call it again? What is it called? I have it on my tongue. So it's basically having yeah, you know how reflection works. What we see, and then it returns. Just a moment. And I'm back again. Just have to find the images of reflection. So basically, what reflection does is actually you. I had the word in my head. Yeah, if we think about the specular reflection, which is basically the mirror-like, it's actually when the ray hits the surface, it goes with the same angle, but in a reverse direction. So it's like, as also in the image, like that. You can probably see it. Same angle in, same angle out, which is what we want to simulate with the reflective surface. I can just show you with the cube here what it actually does. I don't know if it's seeable. The skybox I'm using, or the images I'm using, is from the distributed game Angry Birds. They have skyboxes, so I just basically use those. You see the reflection, but this is not like the light hitting it. It's more or less for this programming is a bit different. So basically the problem we're trying to solve is actually how do we make objects reflective in Unity compared to, and while like using the same things that we know from the real world. In this part we're actually looking at the skybox, which is basically what the texture is on this one. And it's actually the view ray that is actually the one, it's the view one that is actually reflected at a point in the surface, which then and then we have the reflecting ray as we saw in the image. So our view is that way in, and what we see is actually what is actually viewable on the reflected angle. Yeah, that's basically what we can see here. I'll just look into the code a bit. Reflection. So overall, what it does is basically it takes in all the information from our view angle, view direction. It's down here in the vertex output, and this is basically just vertex or vertex shading. Since it's taken the vertex position and the normal vector, and outputs what we need for our calculations. And the vertex output is calculated, it's, as you can see down here, and that's what is interesting actually is that the output is our view direction. Output view direction is what we actually have in taken from the model matrix, the multiplication of our model matrix and input vertex, and we normalize our normal vector and our input, and then we actually just add it together, so it's actually give us like the angle we want. That's what basically does. So why is this useful? This is actually useful for a lot of reasons, because first of all, a lot of people have been working on this in Unity, or in general just knowing how to work with the reflection. Yeah, I'm not going to go into like specifics in the program. It's like, well, it does what it says. It just uses like some basic CG coding. What do we have else that's interesting in here? You'll probably notice that it's only using one pass, because it's the only like component it needs. It doesn't need to take in like with the specular highlighting that it should take into account that it can be multiple lights, and it should just, of course, make sure to like take those inputs separately, instead of having just one main light. Have it to like look at both light sources as the main. But here we only need like basically one, because we have one view ray that we are focused on, which is what we're looking at. And that's more or less that for the reflection. I'll come back and talk a bit about it again after refraction. So refraction, we also know that from like glass or crystals and so on. Like when you look at it, if you take an example like a glass of water and you put a straw in it, you actually notice that what you see in the top is like or from the side, it's like distorted in a certain way. We can also see that in the sphere. It's probably not visible right now, but if we turn around, we can actually see. Let me get a clear view. You can actually see that those are like fixed bars you can see from the reflection, those, and you can see that they're kind of distorted because they have a refraction on it. So what we basically do is then again, like in the reflection skybox over here, we actually have the view ray and use that for like giving the view of it. So it's actually bended a bit. I actually have an image for that. There we go. As you can see, projected light, or you can say that's the view ray if you look at it like that, because this is usually for light. It goes in, and the angle loses a bit, so it's actually a bit skewed. So that's basically what happens in this part. And if we look at the code for refraction, you can actually see how it actually tries to solve this phenomenon. What it basically does is almost the same as reflection, other than the only thing that is like different is actually, yeah, it's basically this part down here. Takes all the outputs there, and it takes from the vertex output as an input, and we have a reflective index as 1.5. That's glass, if I remember correctly, and for this part is actually the only difference that is actually between reflection and refraction is actually that it also needs to normalize the input view direction, or the view direction vertex vector, and also and then will normalize everything else. And this 1.0 is basically just air, so it's actually air divided by the refractive index of glass, and then just return it for our sector cube. I decided to go with a sphere just to like not get confused about it. I can try to put the material on a cube and see. It should do basically the same, so it shouldn't be any issue. That reminds me, I did not talk a bit about the output for reflection. It's pretty simple. It's just reflect the view direction with a normalized normal direction and return that. So it's like nothing special here. So the problem was that we wanted to reflect, what do you call it, reflect and refract the view of a person, so it actually reminds us of, or not reminds us, but simulates how it works in the real world. And I'll say something about it. So we can do that. And Unity, luckily, there's a lot of people been working on it, working on like how to calculate all this different stuff, and already pre-made, so it makes the life easier for other people instead of having to build it from scratch. Program-wise, it's, if you look at the how it actually compiles it, it's actually pretty simple. The only thing it actually needs is it's all the computations are actually done down here. Of course, there's some computation before it, but what we actually need for the reflectiveness is actually down here. And down here for refraction, of course. So basically just solve it by taking in the view ray, as I said before, taking the view ray and outputting it according to like different physics law. The view ray, and that it's skewed because of the index and velocity. And also for reflection, it goes in, it returns basically the same way in, same way out. Don't have anything much more interesting to say about it, other than I think the reason why this way of doing it is actually helpful is that as I said, all the calculations that is needed for like every single pixel can be a tedious task if you do it like hard coded. Luckily, Unity is built so it's actually like high level. Not if you're doing it OpenGL, it's probably going to take a lot more to actually just do it, because as you know, C programming is it's a lot different than just using CG as we're using here, because a lot of things is already done. It's like the vertex and the fragment already built in the CG. Also, all the uniform functions, like the sample cube, which basically says, okay, we are going to work with a cube. So it's basically uniform is just what we are accessing this part, and we are going to call it, of course, cube, something simple. Also, we can use it for other uniform. We can also use for like scaling. Usually, or at least in this example, we're going to use it for scaling. Can also be like, as I said, sampler, cube. We can also sample 2D textures if we're going to do. If we're going to work with textures, bump mapping, and such things. Yeah, basically we don't really have that many like shader options for that sake. Since this is a simple one, had it been like let's say again some of the other types of shading we've done, what is it called again, specular highlights, there's a lot more to it, more not complex, but it's just more you have to do with it. And yeah, that's basically what I have for exactly mentioning that. Option wise, I think it's actually just basically using the vertex again, as I said. Yeah, there's probably something I forgot while I talked. It's like you usually forget something when you're making a video, especially if it's non-scripted at all. So I don't really have any closing comments other than yes, it's actually pretty simple to simulate things we know from the world, like reflection and refraction, and also like fractional. I didn't cover that. This is basically because of I think it's skill level and time being the worst of them, of the bunch. And yeah, maybe I should come around this part again, or basically just shader options. I haven't really talked about that. Just need to yeah, well, shade options allows me. It's basically allowing me to basically work with. I can actually use in some other programs. I haven't been looking. I'm not 100% sure about the shade options used in Unity. It's not a program I've been working with a lot, so but I guess it's basically just using the vertex shading and the pixel shading, because in some other programs. In some other programs, the shade option is basically able to. Some are actually able to turn off the pixel shader for special effects, for example. Like, yeah, it's basically for special effects, like small, what do you call it? What do you call it again? Yeah, particle effects and so on, and lens flares, for example, or something like that. Not entirely sure about the lens flare, but I'm pretty sure about, to a certain degree, sure about the particle effects. So yeah, I don't really have anything else other than I can actually discuss a bit about billboards, but it's not really something that I want to go into, since I think this covered basically a lot already, and time-wise I think we are around the 25-minute mark, so it's probably, I won't go any further with it. So without further ado, this is my walkthrough about this about shaders. As I said before, it's probably something I forgot, or just forgot on the run. You never know. So with that said, thank you so much for listening, and maybe I'll just mumble around with some things or something like that. I apologize for that. Yeah, that's the problem with not having it 100% scripted out exactly what I want to say. So everything is just from the top of my head, and I think that should be the last comment for me. So thank you for listening, and yeah, I don't have any closing remark. So till next time.